What we eat, how we eat, and why we eat are not just habits. They are direct expressions of how our brain and body communicate. Every bite, every craving, every skipped meal, or every binge is a signal. It's a message from the nervous system shaped by stress, past experiences, emotional regulation, and biology. Today, we're diving deep into a subject that's not just scientific. It's deeply personal for millions: healthy eating and eating disorders. When we talk about healthy eating, what we're really referring to is a set of decisions that originate not just in our stomach or taste buds, but in our brain, specifically the circuits that control reward, emotion, impulse, and long-term planning. These circuits are shaped by evolution, by our upbringing, and by our present environment. The brain doesn't simply instruct us what to eat, it negotiates, reacts, reinforces, and sometimes deceives. For many people, healthy eating feels natural, intuitive. For others, it's a daily battle marked by guilt, control, restriction, or overwhelming craving. At the center of this complex equation is the brain-body connection, and understanding it is key to understanding why eating behaviors can become disordered and how they can be restored. From a neuroscience standpoint, the prefrontal cortex, which is responsible for decision-making, inhibition, and goal setting, works in tandem with the limbic system, which manages emotion, memory, and reward. This balance is essential in maintaining healthy eating behavior. When this balance is disrupted by stress, trauma, or prolonged food restriction, eating patterns can become erratic or rigid. For example, individuals struggling with anorexia nervosa often have an overactive prefrontal cortex that overrides hunger signals from the body. In contrast, those experiencing binge eating episodes may have a suppressed or dysregulated prefrontal response, leading to impulsive, emotionally driven eating. These aren't character flaws, they are patterns of neural activity shaped by biology and environment. Equally important is the hypothalamus, a small region in the brain that plays a major role in hunger and satiety. It interprets signals from the body, like leptin and ghrelin, hormones that tell us when to eat and when to stop, and integrates that data with information about emotional state, energy needs, and even light exposure. That's why someone can be physically full yet still feel an intense urge to eat, especially during emotional distress. Or why someone can be starving but feel numb to hunger cues entirely. The hypothalamus doesn't act alone. It responds to upstream influences from the amygdala's fear and anxiety, the hippocampus of memory, and the insulis interoception, or the perception of what's happening inside the body. Together, this network governs how we perceive and respond to food. Another crucial concept in the brain-body dialogue is interoception, the ability to accurately sense internal body states. In people with disordered eating, interoceptive awareness is often blunted or misinterpreted. For instance, hunger might be confused with anxiety, or fullness might be perceived as failure. When interoception is impaired, the body sends signals, but the brain interprets them through a distorted lens. This misalignment often becomes self-reinforcing. The more distorted the internal signals feel, the more control, restriction, or escape behaviors develop, leading to further dysregulation of the brain-body loop. Food itself also affects the brain directly. Processed foods high in sugar and fat cause rapid spikes in dopamine, a neurotransmitter associated with reward and motivation. These spikes create a temporary sense of relief or pleasure, but the brain quickly adapts, leading to tolerance and the need for more food to achieve the same effect. This is one reason binge eating behaviors can feel compulsive. The reward circuitry is firing intensely, even in the absence of real hunger. On the opposite end, chronic food restriction or starvation can elevate cortisol, suppress reproductive hormones, and alter dopamine sensitivity, making it difficult to experience pleasure from food or from life. These shifts are not about willpower, they're about homeostasis, the brain's attempt to restore balance in the face of chronic imbalance. The vagus nerve, often called the information superhighway between the brain and gut, also plays a pivotal role in eating behavior. It sends sensory information from the gut to the brain, helping to regulate digestion, inflammation, and even emotion. When someone experiences chronic stress or trauma, vagal tone can be reduced, impairing this two-way communication. This disruption can cause gastrointestinal symptoms, changes in appetite, and even depressive or anxious symptoms that further influence eating behavior. Training the vagus nerve through techniques like slow nasal breathing, cold exposure, or humming has been shown to improve vagal tone, which in turn enhances digestion, emotional regulation, and the ability to tune into hunger and fullness. Sleep and circadian rhythm are additional factors that influence the brain-body relationship around food. When we're sleep deprived, the brain's impulse control weakens and levels of ghrelin, the hunger hormone, increase, while leptin, responsible for satiety, decreases. This hormonal shift makes high-calorie, high-reward foods more appealing and reduces our ability to regulate intake. Lack of light exposure during the day or too much artificial light at night further disrupts these rhythms, leading to metabolic changes and mood disturbances that can fuel disordered eating cycles. Timing of meals, light exposure, and quality of sleep all feed into the same network of brain-body communication. The human brain is a reward-seeking organ. Its primary objective is to ensure survival, and one of the main ways it accomplishes this is by constantly evaluating what feels good, what reduces stress, and what signals safety. At the center of this process is dopamine, a molecule often oversimplified as the pleasure chemical, but in truth, it's more accurately described as the molecule of motivation and anticipation. Dopamine helps us pursue food, social interaction, achievement, and even substances. In the context of eating disorders like anorexia, bulimia, and binge eating, dopamine is not just misfiring, it's being manipulated by the very behaviors that the brain is supposed to regulate. When someone restricts food intake for long periods, dopamine pathways adapt. In anorexia, for instance, studies show that people can begin to associate the act of not eating with reward. That is, the brain starts releasing dopamine in response to self-denial. What would normally trigger discomfort or anxiety, like skipping meals, begins to feel empowering or even calming. This shift is driven by the brain's remarkable plasticity, but it also illustrates how these disorders hijack the system meant to protect us. The reward no longer comes from nourishment, but from control, numbers, and rituals. Over time, the brain encodes these as habits, and the loop becomes increasingly difficult to break. In contrast, binge eating behaviors involve surges of dopamine in response to highly palatable foods, typically those rich in sugar, salt, and fat. These foods stimulate reward centers more intensely than whole foods, activating the nucleus accumbens and the ventral tegmental area, key areas responsible for reward valuation and reinforcement. After repeated episodes, the brain builds a kind of memory or craving around these food cues. Seeing a wrapper, smelling a particular dish, or even feeling a certain emotion can activate the desire to eat, not because the body needs fuel, but because the brain is anticipating relief or stimulation. Over time, the threshold for dopamine release increases, and the person needs more food or more intensity to feel the same effect. Bulimia represents a painful cycle of both binging and purging, and the neurobiology here is particularly complex. The initial binge stimulates a large release of dopamine and temporarily a calming of the stress response. But the aftermath, feelings of guilt, physical discomfort, or shame, activates the brain's threat detection systems, such as the amygdala and anterior cingulate cortex. In response, purging behavior emerges not only as an attempt to undo the calories, but as a neurochemical effort to reduce emotional distress. This cycle of up-regulation and down-regulation is exhausting for the nervous system, leading to chronic stress, hormonal imbalance, and dysregulation of the hypothalamic pituitary adrenal axis. Stress is one of the most powerful modulators of eating behavior. When cortisol, the primary stress hormone, is elevated over long periods, it can alter appetite, increase cravings, and weaken impulse control. In some individuals, this leads to compulsive eating as a coping mechanism. In others, stress completely shuts down appetite, particularly when paired with high anxiety. What makes eating disorders especially deceptive is that the same behavior, eating or not eating, can serve radically different neurobiological functions depending on the person's internal state. One brain may be seeking control, another might be trying to self-soothe, another may be desensitized entirely. Another component involved is serotonin, a neurotransmitter closely tied to mood, anxiety, and satiety. Low serotonin levels are common in individuals with anorexia and bulimia, and they contribute to obsessive thinking, rigid routines, and heightened sensitivity to emotion. These brain states can lead individuals to view food not as nourishment, but as a source of fear or moral judgment. When food becomes symbolic of success, failure, self-worth, the brain's rational control system is overwhelmed by emotional and automatic responses. The neural networks responsible for thinking clearly are literally overridden by those meant to protect the organism from danger, real or perceived. What's important to recognize is that these patterns don't emerge overnight. They are shaped by repeated behaviors, and those behaviors shape the brain in turn. Neuroplasticity means that the brain is constantly changing in response to experience. The more frequently someone engages in restriction, binging, or purging, the more entrenched the neural pathways become. But the reverse is also true. With intentional change, new behaviors can lay down new patterns. Tools like cognitive behavioral therapy, mindful eating, and nervous system regulation techniques can all contribute to the rewiring process, helping the brain reestablish a balanced and adaptive relationship with food. Impulse control is another domain influenced by brain chemistry. The prefrontal cortex, responsible for executive function and planning, is often underactive during binge episodes or highly stressful situations. This is why someone might plan not to eat a certain food, but in the heat of the moment find themselves unable to stop. It's not a failure of discipline, it's a shift in which part of the brain is in charge. Under emotional duress, control often passes from the rational brain to the more primitive, emotionally reactive parts. Rebuilding the strength of the prefrontal cortex through consistent practice, sleep, and stress regulation becomes essential for long-term change.